Okay. So the second class, we will talk about the RDF model and syntax. So what is RDF? What does RDF stand for? Why do we need this? So we spoke the last time about the semantic web, this idea of structuring the content of the web. And essentially, we talked about the need for data, logic, and querying, structured queries, structured data, to be able to enable this vision. So in terms of the data, that essentially is RDF. RDF is the proposal of a web standards body called the W3C to be able to structure the content of the web to enable these other parts, the logic and the query parts later. So RDF stands for Resource Description Framework, a framework for describing resources. Resources can be anything with identity, people, places, events, you name it. Whatever you can name is a resource. So it's a web standard. It has been recommended by this organization called the W3C, World Wide Web Consortium, for many years. The newest version is called RDF 1.1, and it's been a standard since 2014. The earliest version of RDF has been a standard since 1999. Okay, so we're more or less going to focus on data today. So we're going to describe the standard for publishing data on the web. So RDF is based on triples. So essentially we have this idea precisely that we are making simple sentences that contain just three elements, like Ireland, capital, Dublin. Okay. So the first element is called the subject. The second element is called the predicate. And the third element is called an object. So we can model the world with triples. So we can model pretty much arbitrary data with triples. Not always very succinctly, but we can somehow model anything. So what's nice about triples is that unlike, for example, relational data where we might have to add new tables or new columns or something, to add more data, we just add a new triple. Right? So for example, here we can add information about the population of Dublin, this resource that's mentioned here. This forms essentially a graph. We can draw these triples as a graph where every triple essentially denotes a directed labeled edge. So we have a directed labeled edge between all of the nodes in the graph. So here we see that adding a new triple essentially adds a new edge in the graph, which may be between two new nodes or with one new node, or might have 0 new nodes. It might be an edge between two existing nodes. So we see that every triple represents an edge from subject to object with a directed edge labeled by the predicate. So a set of triples is thus called an RDF graph. So when we talk about a set of triples, we can call it an RDF graph because of this graph-like view that we have for RDF. So why graphs? Where did this come out of? I told you that you know, we need a data model for the web. It would be good to have something that's standard, so we don't have to deal with CSV on one file on one site and Excel on another side and SQL on another site and JSON on another side. It would be nice to have a standard that we could agree on to structure the content of the web. But why graphs? So effectively, why not, for example, tables? Why not trees? Why not some other form of data representation? So I'll argue a little bit for why graphs versus, for example, tables. You might have seen these slides before. I actually teach them in both my other courses, but it's an important note to get across that graphs are flexible. So when we talk about relational databases, often we have different constraints. We have primary key constraints. We have to define a relational schema, and that defines precisely what sorts of data we can add at any given point in time. So somehow they're very well organized, but also quite rigid, quite structured and quite restricted. Okay, So a typical use case would be something like a bank, for example, whose schema rarely changes. They rarely have to add new columns to their tables or add new tables. And the data that they have rarely change. Well, the data, sorry, the values can change, of course, but I mean that the structure of the data in terms of the relational schema doesn't change that much. But if we want to model somehow more diverse data, relational schema can be very restrictive in terms of we need to define upfront before we start adding data, what data we will model. So we have to model our data before we can start to collect data. So if we think about trying to model, for example, information about planets as relational data, we could start with a table called planet, which has a name to start with. We can hopefully name the planets. And we can define the names of the planets as a primary key. So initially, we don't have all our data. We just know that we want to model some data about planets. But later, as we continue, we can maybe start to add some new columns to the table, which would describe distance from the sun, the radius of the planet, normalized by the Earth's radius, the gravity, the length of the days, the years, the temperature, and whether or not it has a ring. Okay, so we fill out a table and we have a typical relational table with, in this case, 7 columns, or 8 columns, and a primary key defined. So this looks pretty straightforward thus far. Now we'd like to model the moons or the satellites, natural satellites of the planets. So, okay, we could think about as a first instance, we could just add a new column to our planet, which is a moon column. We could just add the information about the moons of the planet. However, we see that certain planets do not have moons, or at least they don't have significant moons. So here we have a null symbol. Okay, and in other cases, we can have 2, 3, 4 values. So this is not ideal. So we have to rethink, and essentially we have a 0 normal form table. So we don't even have 1 value per cell in the table. So we would need to rethink this, and we would have to think how we would design our relational schema better. And the response would be to create a new table for moon, right? So this allows us to have a 0 or many relation between planets and moons. So we see that some planets don't appear in the table, other planets do appear once, appear multiple times. So this is great, but here we see there's a small problem. So in entering this information here, instead of using the name of the planet Earth, we use the name of the planet Terra, or Terra, I guess. No, well, wouldn't be that in Spanish either. So Terra. So what we need to do is add somehow. We need to correct this, right? Even to avoid this sort of problem in the first place, what we'd like to say is that this column here should exclusively reference names of planets mentioned here. Yeah. So how we would do that in a relational schema in general would be a foreign key. That comes later. Sorry, we'll come back to that. So to each moon, we add the discoverer as well and the year. Okay, so we see we have a similar problem again because, okay, it's a 0 or 1 relation, right? So we have essentially in this case, each moon has a discoverer here in a year, but in the case of Luna, for example, our moon, the moon of the Earth, who discovered the moon? Who would we enter here, and what year would we enter here? So it's not very clear what information we should put here. So if we want to admit, perhaps, for example, we don't have data about who discovered Charon, the moon of Pluto. So to resolve that, we could again create more tables and so forth. So here we have the problem that we mentioned earlier about Terra being not being mentioned in the original planet table. So what we would like to do is we would like to clean up this sort of situation, and we can add a foreign key. So this essentially says that this column now references the values in this column, and there's no way we can add something here that doesn't reference here. It would give us an error. So when we add this foreign key, we essentially disallow any other names except for the ones that appear here to appear in this column. So therefore we can't have Terra, we have to fix this and we have to replace it with Earth. Okay, so now Pluto is no longer a planet. Okay, great, so we have Pluto here and we need to fix that. So how do we do this? We could just remove the row and forget about Pluto completely. But we have some nice data about Pluto, so maybe we'd like to keep that instead of just deleting the row. So we could consider creating, for example, a second table, dwarf planet, where we have Pluto contained. So, okay. Here we have a problem now because we have our foreign key contains Pluto, and this is a reference to this table here. So how do we address this? How do we solve this? Well, there's actually really no nice solution here. We could try to define, for example, something like a view that's the union of both tables and define the foreign key on top of that, or but it's essentially not very easy to solve this problem. The easiest solution, probably the most practical, would simply be to drop the foreign key and go back to just being careful when we enter in the values of planets here. Okay. So then if we start to think about modeling exoplanets, then we have some exoplanets in terms of planets that orbit other stars. Now we're going to have a major problem, right? So we want to model exoplanets and we have to completely change our relational schema. So at this stage, we get tired of playing with tables. So one thing I could remark here before we continue to graphs is that these tables here, as we continued more and more into the data, we started to normalize the tables by creating these sorts of tables here, where we have sort of a binary relation. This is essentially a graph. So we could consider creating edges from, for example, all the moons here to all of the planets here. Likewise, we could link from moons to discoverers, and we could link from moons to the year in which they were discovered. So these are graphs. So we could call this like a subject column. We could call this the predicate, and we could call this the object column. So as we continue, we've actually been somehow starting to model more and more a graph in our relational schema. In any case, let's have a look at how it looks like if we want to model planets as graphs. Well, if we start with a graph rather than a relational schema, we can just start with a node such as Earth. We can then add another node such as Sun. We can add an edge between these because to represent some sort of relation between them. We can add a label to that edge. And we can continue in that way, adding these labeled edges to represent different types of binary relations between these different nodes. So we continue adding nodes and we continue adding relations. We can add maybe some sort of data type rather than just a thing. We can add numbers. We can continue adding these nodes and we can continue relating them. So now Pluto is no longer a planet. So what do we do? Pluto is no longer a planet. Oh, it's quite straightforward. We can just drop this edge, right? So we just remove that edge. And we can add, if we want, for example, a new node dwarf planet and link Pluto to that. Very straightforward. If we have exoplanets, not the end of the world. We can just add the galaxies to the sun, and we can continue and add other planets and other galaxies, and there's no great drama. So we can continue in this way, and we can just add incrementally more and more data about our planets, and it's much more flexible in the sense that we don't need to define this relational schema at the start. Okay, so in terms of the relational data, the pros and the cons, what are the good parts and the bad parts of using the relational model? The bad news is that we have to impose a schema, a structure from the start. And the good news is that we have a structure or schema imposed from the start. So why is it bad? It's bad because it's less flexible. Why is it good? Because it gives more structure to the data. Essentially, we're always enforcing, for example, that the planets of the moons appear in the planet table, right? So we're maintaining somehow more structure by imposing the schema right from the start. So this is a very much a sort of authoritative, here are the rules that you must follow when you're adding data, or when you are adding new types of data to your relational model. On the other hand, graphs, what are the pros and cons? The pros are that we don't have to impose a structure or schema from the start. And the con is that we don't have a structure imposed from the start. So what does that mean? It means, okay, we're much more flexible, but somehow, you know, people can add whatever data they want now. So it's not necessarily the case that they're going to follow the existing examples. They can introduce new types of predicates, new edge labels. They could do whatever. It could become a mess if, in particular, if the data that are added don't follow the sorts of the precedence of the data that came before. So in general, people will, of course, when they're creating and modeling graph data, try to follow the same patterns that have been used before, and therefore, rather than define the structure from the start, it just sort of organically will appear if people follow the same patterns when they're modeling the data. So it's a much more kind of flexible, organic sort of structure arises from graphs. So thinking as well about the web, the question is, here we just had some simple example involving planets, but imagine if we had to design a relational schema for the web, right? So, or imagine if we had to maintain a relational schema for the web. So if you've done a relational database course, you maybe saw, excuse me, entity relation diagrams, ER diagrams. So imagine sitting down and having to sketch an ER diagram to cover all the content of the web, right? It would seem too restrictive. It seems that really what we want is this somehow this more emergent data structure, this more flexible emergent data structure. So graphs seem like a natural way to be able to model the content of the web. Any questions or doubts? Many of you have probably seen those slides before. I use them in my other courses as well, but it's very important, I think, to understand why we're not using tables. Why not trees? Well, often the main difference between graphs and trees, so trees would be things like JSON or XML. The main difference between graphs and trees is that in graphs we can naturally represent cycles between things. So we can have cycles, for example, between Earth and Sun, or between several different undirected cycles between several moons. In trees, this is not naturally supported. So we wouldn't be able to query easily for cycles, for example, in languages for querying trees. So for this reason, we have graphs. Okay, so hopefully I've given you some arguments as to why it's good to use a graph model to model the data of the web. So we're not done yet, right? So this is essentially, we're getting close to completely describing RDF, but we have to describe how to name things in RDF. So RDF is a directed edge label graph. It's a graph model, effectively. But when we name things, we have to be careful, especially on the web. So effectively, we have to think that strings are not enough. By strings, I mean Pluto or G-type star or Milky Way. So if we look at this graph, we kind of intuitively understand what Milky Way is from context and from our own understanding of the world. And again, we explained in the first lecture that machines don't have that same understanding, right? So if I started to jumble all the letters here in these nodes, then it would become kind of confusing again, right? What is meant. But here we understand what is Milky Way, what is Pluto, what's a dwarf planet, and so forth. So, but what if we were, for example, to think about this chocolate bar? I don't know if you get this in Chile, but you could maybe also consider that Milky Way is a chocolate bar, right? Or that Pluto is the popular character, cartoon character. So, well, essentially we have to be quite careful, right? Because, okay, Pluto, obviously here we wanted to refer to the planet, the dwarf planet. But if we have another graph on the web that describes that Pluto is the dog of Mickey Mouse, and Pluto is an instance of cartoon dog, then we could start to run into problems, right? So if we consider then merging these data from these two different sources on the web, we could end up with some strange looking data, right? So we could perhaps end up concluding that there is a cartoon dog that's orbiting the sun outside the orbit of Neptune. Or we could end up figuring out that this cartoon character Mickey Mouse owns the planet Pluto, right? So we need to be more careful when we name things to avoid these sorts of clashes between names. So what would we use to name things to ensure that we don't have these sorts of clashes? Since we're on the web, it makes a whole lot of sense to use web identifiers. So what do I mean by web identifiers? So you would be very familiar, hopefully, with URLs in terms of uniform resource locations. These are the locations of a resource on the web, and they're most familiar to you probably as the strings you have in the address bar of your browser. Yeah? So HTTP, or more commonly now HTTPS, something as the domain, and then a path that indicates the exact location of the resource, right? So you can use that URL to find the document at that location, the resource at that location. So documents are also resources. You can also name them. However, this is a location of a resource. So this gives the actual somehow physical location of the resource. It says that this document is at this location, right? But we can't really use URLs to identify, for example, Pluto, the cartoon character, or Pluto, the dwarf planet. Why not? Because when we look up that string, it's not going to return us the planet Pluto. It's not going to return us the actual cartoon character, right? It's going to return a document about that. So in the web architecture, there's this notion of more general notion of a URI, a uniform resource identifier. That doesn't need to be a location of something. It doesn't need to say that Pluto, the planet, exists at this location. It can just be an identifier, right? It can just be a name. So essentially, this is a generalization. It's not necessarily a location. It can just be an identifier. Otherwise, it looks pretty much the same as a URL, right? There's no real difference in the string. It's just that it's not really assumed that this is going to give the location of the resource that it names. And finally, since this sort of percent encoding here is quite ugly, a newer generalization to be able to move away from being sort of ASCII English centric is towards IRIs that allow that have URIs that allow for Unicode characters to move away from a bias towards Latin alphabets. So you could also have Chinese, Japanese, or whatever alphabet you could use here in your IRIs. So these are, again, our identifiers that we can use to identify arbitrary things. So since we're on the web, we're going to identify things using web identifiers, similar to what we use for documents, but somehow more generalized. Okay, any questions or doubts? Okay, so writing out IRIs are very long with HTTP, blah, blah, blah. So it's very common in the context of RDF to use prefixes. So to use, for example, a local prefix like example, which we define somewhere. We define in some part of the document, and then a local name. So this allows us to define multiple IRIs within the same, what we would call a namespace. So a namespace is just a kind of prefix. So here, when I write this sort of thing here, you should interpret this as a web identifier, as an IRI. Okay, so this will be expanded out into the full form here. So we don't have to write out full IRIs every time. So there's some frequently used prefixes. If you see these prefixes here, this is how they're defined. I'm not going to otherwise talk too much about that. So we'll leave this for reference. So we can move from strings now. We can start to use web identifiers to identify things. So rather than just simple strings like Ireland and Europe and Dublin and so forth, we can create these IRIs. in an example namespace. Okay? So now we have these web identifiers. We have a namespace that we can use for naming things. So we still see that more or less we can still read the graph, okay? But this time we have these web identifiers that should have less, should lead to fewer clashes in general if we're careful about what namespaces we use between things. So what about, what about the population here? So we didn't assign an IRI to the number. So is it a good idea to assign, should we assign web identifiers to numbers and to Booleans and so forth? You could, right? You could potentially assign an IRI for every natural number. It would create a lot of IRIs, but you could do that. But, sorry. You could do that, but it would lead to a lot of IRIs. It would lead to quite a mess. So as well, these sorts of values are of a special character because the machines can understand these values. It has some meaning. They can actually parse these numbers, and then they can take two numbers with the syntax and they can somehow compare them. They can add them, they can multiply them, and so forth. So these sorts of data type values have some special meaning, or they can be processed in a special way by machines. And if we assign them IRIs, we would lose that, right? So actually it's better, instead of using IRIs, to allow data type values in RDF, things like strings and numbers and Booleans and dates and times. And we can define then special functions so that the machine can do things like extract the year from a date, compare different times, and so forth. So these are only allowed in the object position. So the idea is that we're not really going to describe a string normally. This is mostly for historical reasons. We could think about doing this, and there's lots of arguments that this is not fully general, that you could have literals and objects. But for historical reasons in RDF, we don't allow them in objects. They might be a little bit weird in predicates, okay? But so essentially, this here is correct, and these two here are incorrect, okay? So we can have a number or a data type value as an object, but not as a subject or a predicate. So what kinds of values can we have? Or how do we describe these data type values? So when we serialize them, what we're going to have is a lexical string followed by a data type IRI. So for example, 200, and we have these double corrects here, and then we have the IRI of the data type. Again, this will expand out into a full HTTP :// IRI. But we have a special namespace called XSD, XML schema data types, which we'll talk about in a second. So we have a lexical string, and then we have a data type IRI that indicates how that lexical string should be encoded. So by default, if the data type is omitted, then it's a string. So by default, if we don't have a data type IRI, we will consider the data type to be a string. So there's a whole bunch of types defined by a standard called XML schema. I'm not going to talk in too much detail about all the types, but we can, since we're at 10:45, we can take a break. And afterwards, I'll talk about some of the different groups of types that we have in a high level. If there's any questions or comments, I'm happy to take them. Oh.
Profesor, yo tengo una pregunta.
You can also ask in Spanish if you prefer. No problem.
¿Me escucha?
Okay, let's see the chat. So we'll stop screen and pause recording. So seems I had a problem with my audio. I hopefully should be able to hear now. If you'd like to ask, sorry about that. Any questions? No? Could someone say, or just as a test, just to make sure I can hear? I should be able to test my audio and stuff.
Hello, profe. ¿Se escucha?
Yep. Thank you. Yeah. Okay. So I can hear you now. So data types. So many of the data types are borrowed from XML schema. So we have a lot of types. I'm not going to get into them in detail, but there's essentially four categories we could consider. We have Boolean data types, which can be true or false. 1 or 0 is also considered, it is also allowed. So we could say if something is true or false. We have numeric data types, where we have a lot of numeric data types, referring to different types of programming language data types like non-negative integers, positive integers, unsigned longs, and so forth. We also have approximate values. So that would be doubles and floats, for example, which are floating point numbers. So this tree here, this sort of hierarchy, refers to types that are inherited from other types. So this means that a byte is somehow a restriction of short, which is a restriction of int, or in other words, every byte is also a valid short, int, long, integer, and decimal. Doubles and floats are not on the same branch because these are considered to be exact values. And these here are considered to be approximate values with different forms of approximation based on floating point numbers. So we see here the different types we have. We have some examples of different valid lexical strings and some notes about their precision. So, okay, so we have, for example, Dublin's population is an integer, 1 of 1 million. Okay, we also have temporal data types, where briefly we have times, dates, date times. We have date timestamp, where we must add the time zone. This makes date timestamps gives them a total order, meaning that we can compare any two date timestamps. If we have a date time and we don't have the time zone, we might have some ambiguity about which came first, because it will depend on the time zone that's not given. We have durations in terms of date times. If we want to measure long durations or shorter durations, sorry, or we can have year-month duration, which is a longer duration. We have data types to specify a day of the month, a month of the year, a month day, a year, or a year month. So for example, if we wanted to specify what the time at which a class begins, we might indicate, for example, time. If we wanted to indicate a birthday of somebody, we could consider using, which would we use if we consider birthday? It would be month day, right? Because it's sort of reoccurring every year. So we could consider using month day to represent birthday. So we have various temporal data types for representing different times and durations and dates. We have some text and string data types. Some of these are just specific to XML. They're not really so interesting. Mainly the one that we'll mostly use here will be string. Okay, we're often not going to use any of these here. We have a data type for valid IRI strings. We have a data type for valid HTML strings. And we have also a data type for valid XML strings. But in general, the one that we'll most commonly use here will just be string, XSD string, and we don't need to explicitly specify it. It will be understood by default that it's a string. Okay, so aside from data type strings, we can also have language tagged strings. So we can specify that a string is in a given language. So on the web, of course, we might have different text in different languages, and we want to be able to deal with this sort of multilingual content. So what we can do is we can add an arroba, an at, and specify a language tag. For example, EN or ES in this case, to specify that the name is in Spanish or in English. So what's the syntax? We just have a string and then we have a language tag associated to it. So in general, you do not need to specify a data type for this. So once you have this @ symbol, it's understood to be a language tag string. So that's essentially literals. We have plain literals, which have no data type or language, and they're understood to be strings. We have data type literals that can be Booleans, numerics, dates, times, strings, and we have language tag strings with which we can use to associate different languages to different text. Any questions or comments? Okay, so we have a third type of term. So we've seen IRIs, we've seen data types, or we've seen literals. The third type of term that we can use, the third and last type of term we can use in RDF are blank notes. So we can use blank notes in RDF. So essentially, if we have to name everything in an RDF graph, it can be somehow a lot of work, right? So somehow there are certain things that, certain nodes that we might use that are not so important to name. We can just somehow say that there exists something here, and we don't need to assign it an IRI. We don't need to assign it a literal, a data type literal, for example. We can just say, okay, here's some node. So how does this work? We have, in general, the syntax is we'll use underscore and as a sort of a blank namespace. This will indicate a blank node. So it represents the existence of something, and often it's just used if we don't want to name everything, or if we have a syntax where we want to map that syntax to graphs and fill in some blanks, we can use blank nodes for that. So it can only appear in the subject or object position. So it's going to be a little bit mysterious for the moment. I'm going to leave it like that, but we'll come back and see some examples of where we might use blank nodes a little bit later. So we can use them in the subject or object position. Okay, so here or here, but not in the predicate. This will not be allowed. So the first two are correct, and the last one is incorrect. So okay, this is maybe a little bit mysterious for now, but we'll come back to blank nodes. So as a summary, we have three types of RDF terms. IRIs are used to name generic things or resources. Literals, which are used to indicate data type values, strings, numbers, integers, and so forth. We can also have language type strings if we have strings that refer to natural language. And we have blank notes, which are used to avoid naming things. It's often used for shortcuts or for indicating the existence of something that's not known. Okay, so in summary, in subject, we can have an IRI or a blank node. Predicate has to be an IRI always, and the object an IRI, a blank node, or a literal. This is mostly for historical reasons, but it's also reflects the most common ways in which RDF will be used. Okay, so let's talk about modeling a bit of data in RDF, how we might model some real web content in RDF. So we have a brief description of some movies. Sharknado is the first movie of the Sharknado series. It first aired on July 11th, 2013. The movie stars Tara Reid and Ian Ziering. The movie was followed by another one called Sharknado 2, the second one. Okay. So what we would like to do would be to model this content, not as text, but rather structured as RDF, right? So we will essentially model it as a graph. Okay, so this is something we normally do in the whiteboard, which might be a little bit awkward, but we could maybe first try to identify the nodes. So what would be the nodes of our RDF graph here? So any ideas of some nodes that we'll start to model?
Sharknado.
Yep, so we start with Sharknado, and the next one might be, we should probably indicate maybe that it's a movie. We might use a node to represent the idea of a movie. Sharknado series for sure will be there. We could represent the date as a node using a data type literal, and then we can model these people as nodes, and then we can model the second movie as a node. And then we just need to connect them with their different relations. So we have Sharknado series, which we know to be a series. Okay, so since the text explicitly mentions that it's a series, we'll add this. So we use this special property here, which is part of the RDF standard. It's so common that in the RDF standard, they actually define this term, which is RDF type. And this essentially allows for associating an instance to a class. So for example, we can say that Sharknado is a movie. It's essentially an is-a relation. And since it's so common, instead of having 100 different properties for this across the web, in the standard itself, it's defined this property. So we say that Sharknado series is a series. The first movie is Sharknado. Okay. It aired on July 11th, 2013. So we create that with a data type literal, and we give the relation first aired between Sharknado and the date. The movie stars Tara Reid. Here's Tara Reid here. Here's Ian Ziering. So we say that we add a stars, an edge labeled stars between the movie and Tara and Ian. We say that, okay, that Tara and Ian are actors, which is not 100% necessary, but okay. We say that Sharknado 2 is the other movie. We say it's the second movie of the series. So here we've opted not to add this relation followed by. So there's no followed by relation between these two. Rather, we consider it to be implicit somehow in the two relations here. So the second movie will follow the first movie. We could, if we wished, add an edge here, but somehow that's already encoded from these two relations here, that this movie follows this one. So we see as well that we have labels. So it's important in general not just to give the IRI, even if we can sort of read the IRI and see what it says. It's important to give labels to the nodes, right? So to give the string the name in whatever language. So we don't do that we should do this for pretty much all nodes. We should always give a label, a name in a human readable format for our nodes. But since that would just create a lot of different nodes here, we'd kind of fill up all the slides. So here, just give some examples. So we have some human readable labels for the nodes. So we see this is pretty intuitive. It has some drawbacks. There's one or two things that are not great here. One thing that's not great is this first movie, second movie business. So because we want to just say that these are movies of the series, and we want to say that somehow this one came before this one. The problem with it is if we wanted to search for all the movies of the Sharknado series, if we imagine querying for it, we'd have to do something like first movie or second movie or third movie or fourth movie or fifth movie, which is not great. If we wanted to specifically find where a movie came in a series, we would also like to maybe have, like, for example, the number 2 for Sharknado 2. We don't have that directly represented. We'd somehow need to map second movie to a number 2, and it's a little bit messy, but we can see other ways of modeling this sort of data. But as a quick indication, in RDF, since it's unordered, it's a set of triples. One thing that's slightly awkward to represent is order, like which came before which. Okay, so we'll see a standard way of doing that later, and there's a few options to get around that. So in general, hopefully it looks pretty intuitive in terms of what we've modeled. This is similar to what you'll be doing in lab 2. You'll be taking some description like this and modeling that description as RDF. Any questions or doubts? Okay, so this is a relatively straightforward example, except for maybe this order thing here, which is a little bit tricky. So we have RDF terms used as predicate, right? So we have IRIs always as predicate. And we have, here we have classes. Sorry, these are called properties, I should mention. These terms here that we use in the predicate position are called properties. So these are the terms themselves. So we use predicate to refer to the middle position, like it's a position almost in the table, or it's a middle position of a triple, and we we refer to the terms used in that position as a property. Okay. We also have classes, which are the terms used to kind of group resources that are somehow conceptually similar. for example, to group movies, actors, and series, and we use the property or predicate RDF type to indicate the type of a resource. Okay. So, for example, Sharknado type movie. So these two types of terms are quite general, and they offer somehow a way to understand the structure of the data. So we can, for example, define properties and classes for a given domain, and publish that online, and we can share that with other people and hope that they use similar properties and classes. And the result will be graphs that are somehow interoperable or compatible with each other. So if every website uses a different class for movie, it becomes more difficult somehow to integrate that data later. But if we publish somehow and encourage people to use the same classes and the same properties across the web for the same things, then we can start to get some additional interoperability, or make it easier to integrate the different types of data. So this is something we'll come back to again in the next class, in terms of defining these properties and classes, what they mean. So the example we saw was relatively simple. What we'd like to do is look at a more complex example of modeling where it's not so simple in RDF. So we have this claim here, and what we'd like to do is to model it in RDF. So we would like to model the claim that Batman Returns stars Michael Keaton in the role of Batman. So, okay. So how would we think about doing this? So to start with, our notes would be, let's see. So we have Batman Returns. This is very difficult, but hopefully, so long as it's readable, I'm happy enough. We have Batman, and we have Michael Keaton. It's hopefully more or less obvious that these would be the nodes. So how do we connect these things? Okay, so we could connect things as we did before, right? So we could say that Batman Returns stars Michael Keaton, and somehow maybe connect Michael Keaton to Batman and say role, or maybe we could even connect, so we could connect, for example, maybe Batman Returns to Batman and say something like character as well. Okay. So this is pretty straightforward and pretty direct. There's nothing so complicated here. Can anyone see any possible downside of modeling like this? Okay, so in this specific case, we know Michael Keaton interpreted this role. We know that this role is a character in this movie, and we know that this movie stars Michael Keaton. So just with this example alone, we're okay, right? Okay, so here I didn't bother adding the, okay, so I did it slightly differently, but I didn't add this stars relation here, which we could almost interpret as being given by this under certain circumstances, right? But what happens if we have, for example, multiple people interpreting the same role in different movies, right? So now we have Batman Begins as character Batman, Batman Returns as character Batman, Batman is played by Michael Keaton and Christian Bale. Can anyone see the problem?
¿Quién se identifica en qué película actuó cada actor?
Right. So we don't know if Michael Keaton was in Batman Begins or Christian Bale was in Batman Returns, or which movie these people were in. So we have to resolve that. So one way we could think about resolving that would be, we've seen the problem. One way we could think about resolving that is to add additional edges like we saw originally, right, between the movie and the actor. So now we know that the actor starred in the movie and which character they played, right? But we can have more complex scenarios where okay, what happens if we have multiple characters playing multiple actors, multiple movies, right? And then we're going to have a problem. So here, this is hypothetical, but let's assume that Christian Bale also played Robin in Batman Returns with Michael Keaton, and Michael Keaton played Robin in Batman Begins with Christian Bale. Okay, so obviously hypothetical, but now we end up with this sort of mess here of edges, right? So we do the same thing as we did before, but now we have these two characters, Batman and Robin, and we see that we have to connect both movies to both characters, and we have to connect both actors to both movies, and then we need to also connect the characters or the actors to the stars relation, which I don't think I've completely done here. Actually, I think I'm missing an edge, but in any case, so we need to connect everything to everything, right? And again, we lose the information about which actor played which character in which movie. So which character played which actor played which character in which movie, we don't know. So rather what we'd like to do would be to represent the interpretation of a role in a movie as a resource. We would like to view somehow Michael Keaton's interpretation of Batman in Batman Returns as a resource, as a node in the graph, and connect that node to the different information. So this is a typical way where we would like to represent what are called n-ary relations, where we are relating more than two things. So in this case, we are relating a movie, an actor, and a role. Okay. So how would this look? Essentially, what we'll have is somehow a new node. We could name this Batman. Michael Keaton interprets Batman in Batman Returns. You know, we could add all of that together and stick it into an IRI or encode it as a hash or something like that. But here we can simply use a blank node, and we can say, okay, this blank node here refers to essentially the existence of this interpretation. So we know that there was something that was played by Michael Keaton, who had the character Batman in the movie Batman Returns. So this node essentially here refers to the interpretation. So we can model n-ary relations in a graph simply by considering n-ary relations to be something, a resource, right, that we will assign a node. And then we connect that node to all the different participants of the relation, the things in the relation we want to connect. So with this, we see we should have no problem with having multiple actors in multiple movies interpreting multiple characters or the same characters. So this is an example of modeling more complex data. So we have another case, which is modeling RDF. We're modeling in RDF, we have an unordered set of triples, so it can be difficult to represent order. For example, the first, the second, and the third movie. We saw one way, which was this way of adding these properties, first movie, second movie, third movie, but we can see that it's going to be kind of awkward to query this or to somehow to process such data. So is there a more general way to represent lists as a graph? So RDF, the standard actually proposes one way, which is called RDF lists or RDF collections. So the idea is essentially much like the data structure of a linked list that you might have seen in a course before. What we're going to do is set up essentially nodes that refer to lists. So this list here, we denote is the empty list. We denote, sorry, this list here refers to the empty list, RDF nil. So essentially what we do is we link sublists to their, we link lists to their sublist. So this is also a list node here, and it indicates its first element, and then it indicates the sublist that continues it, okay? So here we have another list node, and this indicates its sublist, and it indicates its first element, and so forth. So what we have essentially is a list where we have 1, 2, 3 elements. And somehow by having these nodes, we can represent order, and we can also end a list. So we can represent in this way lists of things using the graph structure itself. Now, there is quite some debate in the RDF community. This being a research course, there's these things are still not, there's still lots of debate about how best to design this, and there's lots of debate that this should rather be a data type, like we should rather have a data type which is an array of things to be able to handle this more carefully. Why? Because this is slightly difficult to query and to process. But this is the standard way defined thus far for modeling this in RDF. There are other alternatives that have been proposed. So once we have this standard way, of course, we're not just using this for this one example of, modeling the movies in order of the Sharknado series, which of course is a very important use case. But we can also use the same vocabulary, the same sort of modeling, for example, for the ingredients of a recipe to indicate that we should first add sugar and then water and then add lemon to make lemonade, because otherwise it won't taste good. So we can use this list for modeling general lists in RDF. So here we use as well the blank notes. We don't want to really name every element of sublist with an IRI. So here we just somehow use these blank notes as a glue to really connect the things we're interested in. This is sort of a more syntactic node, but we're more interested in lemonade and sugar and water and lemon than we are with these sort of syntactic glue elements here. So that's a very common use case in which we might use blank notes. Any questions or comments? Okay, so we're nearly there. I'll have to finish the class on Wednesday. What I'd like to end with is just the idea that blank notes add complexity. So while blank notes can be useful, essentially it avoids having to assign everything in IRI all the time, which is quite useful if there's notes that we don't really care about that are more syntactic, or if we just want to represent the existence of something. They can cause problems. So here we have some RDF graph that represents recipes with their ingredients. And actually, in this case, we don't even know what the ingredient is, we could imagine. We just know that it contains some ingredient that has citrus, okay? And it has some ingredient that contains gluten. This could be useful for allergy information, for example. And pecan pie has some ingredient that contains gluten, and pecan pie has some ingredient that contains pecan. So if we were to consider merging somehow, taking these two graphs and integrating them, sticking them together, if we were to do this in the sort of naive way to combine these two graphs, what we would end up with is an RDF graph that looks like this, which is maybe not really the intention. So we match this B2 to this B2 here, and we create this super ingredient that contains both pecan and citrus, which is not really, these blank notes are not interpreted like IRIs. They're not interpreted as identifiers. They're just interpreted somehow as these labels that we use locally in the graph. We don't want this to happen. So blank notes are defined as local variables. They're local to a particular RDF graph. So a particular RDF document, for example. So if we have B1 in an RDF document on one RDF document on the web and B1 in another RDF document on the web, they're not considered to be the same thing. So how should we really combine these two RDF graphs? What we should do is relabel the blank notes in each graph such that the two documents don't share blank notes. So we can do this in any arbitrary way. So the labels of the blank notes are just like the variables in a programming language, or variables in a query or something like that. It really doesn't matter what they're called, they just have this sort of local scope, right? So we can just rename the blank notes to make sure that we don't have a blank note clash. We don't have the same blank note in both documents. How do we do this here? We just, for example, add G1 here and G2 here for the second document, and then we can take the union of both. And we see that we don't interpret the merge of the two graphs as containing, as with the super ingredient that contains citrus and pecan. Okay, so this is a much better way. This is called an RDF merge for combining two RDF graphs. And this is a non-trivial aspect of the data model as well, which is that we can take two graphs, and to combine them, we just do this union, essentially, making sure that we keep the blank notes distinct. We just take both sets of triples and take the union of the sets of triples, making sure not to merge any blank notes across two documents. So this is also a major benefit of using graphs. So blank note names aren't important. So it means essentially there's this notion of isomorphism, which means that the two graphs are equivalent up to blank node labels. So essentially here we don't really care so much these labels, whether they're BZ or L3, L2, L1, it doesn't really matter. Yeah, we don't really care. So essentially what this isomorphism says is that these two RDF graphs have the same structure. They have the same content. Yeah. They're structurally the same. We don't really care so much about these variables, the precise names of those variables. So we see that these are isomorphic. So we see that in this case, the two graphs are not isomorphic. So why are they not isomorphic? Because somehow this is swapped, right? Now we have lemon connected through this node to lemonade, whereas that's not the case, right? Here, sugar is connected through this node to lemonade. So these graphs are not isomorphic. They have to be, we have to be able to make one graph into the other by relabeling or renaming the blank nodes in a one-to-one manner. So we can map L1 to be X, L2 to be Y, L3 to be Z, and we have exactly the same graph. That's not the case here. Right? So we have this notion of isomorphism, which you might have seen in another course, maybe, graph isomorphism. So it's this question of if two RDF graphs are the same. So some cases look quite easy. If we take these two cases here, we can kind of look at it, stare at it for a minute and say, okay, we could probably map B1 to NB here and B2 to NA here, even though we've drawn them in different ways. And we could say, okay, these are equivalent. We could convince ourselves of that, even though we've tried to be tricky by drawing them different. So in general, this doesn't seem to be too difficult. But in fact, this is a difficult problem. So to see that it's a difficult problem, we have a more difficult example here. And the question is, are these two RDF graphs isomorphic? Are they the same? So here I haven't given a label, but we just assume that every edge here has the predicate P. So what do you think? Are the two graphs isomorphic? So it's not clear, right? So the answer is that they are actually isomorphic, which you can verify with this. So for example, this node here, the blue node, matches it links to the yellow node, which links to the pink node, and so forth. So you can see that the structure of the graph is the same. It's just been drawn differently. But this is a hard problem. This problem of figuring out if two graphs, two RDF graphs are isomorphic, is known to be GI complete, which is this complexity class where GI is sort of cheating. It stands for graph isomorphism. So it's an intermediate problem. That's, if you've heard of P and NP, it's the graph isomorphism is not known to be in P, but it's not known to be NP complete either. It's somehow between these two classes. So in general, the message is that it's a hard problem. And this is introduced by the notion of blank nodes. So we can leave it there for now. I'm slightly over time again, sorry. So I'll take any questions or comments. So the main message with this isomorphism is just that the blank nodes look convenient, but they actually introduce some theoretical and practical complications when we deal with RDF. So in the class on Wednesday, what's left in the class is just to discuss a little bit some of the syntaxes that we can use for describing RDF. In the lab on Wednesday, I will give you some text, or Jaime is preparing a lab where we'll give you some text, and we'll ask you to model the content of that text as RDF. Any questions or comments? No? Okay. So if there's no questions or comments, we can chat on Wednesday. Sorry for the audio at the start of the class as well. I'll make sure to test my audio before the next classes. So see you on Wednesday.